Okay, good afternoon. Thank you for coming to our seminar series. Before starting our seminar, I want to notice one thing. Here are some important notice about this seminar. I just talked. Reproduction is prohibited. Reproducing all or any part of the content is prohibited without the author's permission. This seminar will be recorded and the video will be available on the Weekend AIP website later. So if you have any questions or comments, please scroll to the bottom of the page and click the Q&A tab. You can put questions or comments in the box. So if you have any questions, please type your comments in the chat window. So if you have any questions or comments, please scroll to the bottom of the page and click to the Q&A. Oh, so this is again the same. Okay. And so this is like another AIP Open Seminar. So this is like nice AIP seminar with the high dimensional statistical modeling team. So after this, we have several AIP seminars. So next week is with a functional analytics learning unit. I will advertise this one later, but actually we have a lots of seminars later. So please join to the other seminars as well. Okay, so then let's start. So thank you again for coming to our seminar. I'm a PI of the high dimensional statistical model. I'm Makoto. And if you have any questions for this this talk, please send me an email here. So, okay. Okay, so in our team, we are mainly focusing on the scientific discovery using machine learning. So here is one of the examples of the scientific discovery, high-level idea. So here we want to discover important information from complex data. For example, we have some, this is the image of gene expression data. Have some gene expression data with some labels. Sometimes we have labels, sometimes we have not labeled. And then we want to find some important target genes, and then maybe this can be used for the drug discovery, for example. And actually, we want to automatically do this using machine learning. So in our team, we consist of several other. So we have machine learning team, me, Tam Lee, and Benjamin from Osaka University and the visiting scholar, and Dinesh from the postdoc. And we have several other part-time students. In particular, the Ryoma is the contribute to our projects a lot. And there's many visiting researchers in machine learning. In machine learning side, we are working for the feature selection, optimal transport, and graph neural networks. And for the science side, we are mainly targeting some very scientific problems. For example, one of the big topic now is like how to cure acute myeloid leukemia. And also some members working for genome-wide association studies and the biomedical image analysis. So for this science side, we have Hector. Hector is, he's also postdoc in our team. He's working for the GWAS association study. Also from next year, we have another member from he's Peter. He is working for biomedical image analysis. And we have a lot of collaborators to work for this side. And actually we have, our team is consists of machine learning and science, and we are really targeting on this field. And in particular, we are really interested for develop machine learning methods to scientists find new scientific discoveries. We really want to deliver something really important scientific discoveries by using machine learning. So also we are interested for the biological data. And the key challenges in biological data is, so biological data, or like many scientific data, is highly complex. So linear model might not work. And so therefore, we want to use nonlinear model, but nonlinear model is too complex. And so in particular, if you want to use the nonlinear model to some science domain, and scientists may not want to use such a very highly complex things. In particular, the deep methods may not be a good choice for that, right? Also, for such a data, like scalability with respect to number of features is very important. Also, for the biological data, heterogeneity is always the problem. And so this is mainly the technical challenge. Also, in addition to this, like in particular from machine learning side, the collaboration with other domain is also very, very difficult in general. But actually, we are somehow make it work. So this is our team strategy. So we believe, so we need to solve three big problems. One is for the complex data analysis, in particular nonlinear models. And because the biological data is highly complex. And in addition to that, because in biological data, basically the number of samples, number of points is very small. So in general, we expect to have 1,000 to 10,000 data points. But actually, if we work together with the real programs, we tend to have 10 to 20, like very small number of points. So therefore, we need to some new methods to somehow integrate all the data points somehow in a nice way. So in this direction, we are mainly working for the optimal transport problems. We believe this can be used for such a problem. And the last piece is the human in the loop. Of course, if we just use some machine learning models, we can solve the real problems. So therefore, we really need the specialists to join to our project. And then we really want to solve this part of problem. Okay, I want to introduce some of our recent works. And so in our team, we are mainly working for the nonlinear feature selection. I have been working for like the nonlinear feature selection method called the AIP cluster since 2012. And we have developed this. So this is like AIP cluster formulation, but here, because I don't have lots of time, I just skip the details, but this is some sort of lasso problem. And so if you're interested to use this method, please install this package. This is the pip installable. And we have been working for this, like AIP cluster, block AIP cluster. And recently, we actually showed some theoretical results of AIP cluster. So this is like a talk, the topics of Benjamin will talk later. We also work for the post-selection inference for kernels. So this is some sort of selective inference programs. So this is a work together with the Professor Ichiro Takeuchi for another Riken AIP team. And so far, we have been working for some kernel or linear-based methods. But of course, like we, as a scientific challenge, we just wonder whether the deep model can be really useful for such a high-dimensional data. So for such a problem, we are recently working for the DNN-based method. And actually, for the postdoc Dinesh, he proposed a new method called feature selection networks. He will talk this one later in details in his presentation. Okay, so this is the first part. And so in addition to this, we are working for the graph neural networks. So for the graph neural networks, we have been working for the theoretical analysis of GNN and random feature-based GNN. So this is some sort of like random feature-based initialization of GNN. Also, we have developed the constant time algorithm for GNN. This can help GNN scalable. And for this part, it's mainly work done by Ryoma Sato. So if you have any further question for this part, please contact him. So this is like a GNN theory and some algorithm. In addition to this, we are recently working on some graph GNN explanation called GraphLine. So this is one of the very simple interpretation method for GNN. Okay, so this is the first part. The second part is optimal transport. So the optimal transport, we also have some history for working on these topics. So I started working on this one since 2011. So that time I worked for the cross-domain object matching. So this is actually the formula as density ratio and optimal transport. And so this optimal transport can be used for something like many problems in machine learning. And actually, this is very popular, one of the popular machine learning topics nowadays. So one of the application would be like semantic correspondence. So this is we have two images, and we want to find the correspondence between two images. Also, in our team, we are working for the high-dimensional optimal transport problems. So this is something like a mixture of the feature selection and the optimal transport problem. So this is some like optimal transport problem in our team, but the main topic in our team is the optimal transport on tree. So this is the largest topic in our team. So for this one, we have been working for the proposed sliced tree Wasserstein, unbalanced OT on tree, like Gromos Wasserstein version of tree, by recent application to the neural architecture search. For this part, Tam will mainly talk about sliced tree Wasserstein and some unbalanced OT on tree. So this is currently under review. So he will talk this part later. Okay, so another thing is we are also working for machine learning applications and collaboration. So far we have done several other things. First one is like image activated cell sorting. So this one I helped to develop some CNN-based cell image classification module. Also, we have been working for the materials informatics and metabolic data prediction. So this task we have used the HC lasso, and actually we got pretty good performance. So this one is a collaboration with the Tsuda team, and this one is collaboration with Tamiya team. And for the also recently Hector, so he joined to our team, and then he's working for some GWAS program, and he will present about network guided genome-wide association studies. So this is on bioRxiv, and hopefully will be appear pretty soon. Also, actually, we are collaborating many other research teams, so more results coming soon. Okay, so this is a brief introduction of what we have been working on in our team. So this is the schedule. So first, Benjamin talked about some theory for the HC lasso or some nonlinear models, and then Dinesh will talk about some deep learning for a method for high-dimensional data, and the Tam talk about some optimal transport, and in the end, Hector will talk about GWAS data with the network analysis. So this is the end of my slide, the talk. Thank you very much. Then please, Benjamin, please prepare your presentation.
Thanks very much for joining this seminar. It's a great pleasure to present this research work, which is a joint project with Makoto Yamada. So I'm from Osaka University and visiting scientist at Beacon. So the agenda of this presentation is as follows. So first, I'll introduce the proposed method. So the HSeq, sparse HSeq method. I'll go over some theoretical results, and I'll illustrate these results and the relevance of the method through some numerical experiments. So let me say a few comments about the concept of high-dimensional statistics, and with the following two slides. And first of all, on the concept of big data. So I guess that most of you have heard about big data. So basically, nowadays, we have access to new types of data. For example, in the insurance sector, we have this type of continuous geolocation of car drivers through the GPS system, in which companies are interested in order to fix to set the premium. Facial recognition. In finance also, we've got a continuous, an almost continuous measurement of financial assets. So they are at the milliseconds. We've got new price observations and the like, of course. So the common feature of these types of data is that they are massive, okay, and large data sets may allow for more flexible relationships than the simple linear regression approach. So basically, they require new statistical methods to analyze the relationship among these data sets, to draw meaningful conclusions and perform prediction. So one of the key concepts in high-dimensional statistics is the concept of variable selection, which will accompany us in this talk. So roughly speaking, the problem is the following one. We have an outcome of interest, Y, and we have a set of covariates, features. And this set can potentially be very large. So the issue is to learn about the conditional distribution. So Y given these covariates. And here the issue is to ensure that we can select the truly important features with few mistakes. So maybe let me precise what I mean by important or unimportant feature. So an unimportant variable, xk, is characterized by the fact that the conditional distribution Y given the covariates does not depend on this specific covariate xk. So this is roughly speaking what I mean by unimportant variable. And high dimensionality in this talk is about the large number of parameters that we would like to estimate, and it concerns variable selection, feature selection. So a lot of methods were proposed to perform feature selection. So here I list the three main families. So the first approach, and probably the most commonly used method, is the lasso-based method to perform variable selection, and most of the time within the linear regression model. So basically it consists in setting to zero some parameters, okay, in order to exclude the unimportant covariates. But there were some additional methods which were developed and which are nonlinear methods. The first main approach is the so-called sparse additive model, or SPAM, where the outcome of interest is specified as a sparse linear combination of nonlinear functions based on kernels. So the key assumption here is that SPAM is based on the additivity assumption, additivity over the selected features, which makes difficult the identification of the truly important features when the outcome cannot be modeled as additive functions of the input features. And the alternative approach to perform feature selection is the screening approach. So this method consists in selecting the important features by ranking what's called an association measure between the feature and the corresponding output. So the association measure, I will say a few words about this later. Basically, it's a dependence measure between the output and the covariates. So a non-parametric model will be fitted to the screened features, screened between the covariates, the features, and the output. And this method selects features if a relationship exists between a feature and the output. So, as I mentioned, the association measure used in the screening method is a measure of dependence between the output and the feature, and a broad range of association measures were proposed in the literature. So here are the three main ones. You can find alternative measures, of course. So here I just list the three main ones: the mutual information, the distance correlation, and the measure which will accompany us here, the Hilbert-Schmidt independence criterion, so which was developed by Gretton and co-authors. So one of the key limitations actually of the screening procedure is the tendency to select redundant features when a significant number of similar features are related to the output. So this is a key drawback. So to fix this issue, the so-called minimum redundancy, maximum relevance feature selection method was proposed to tackle this specific redundancy issue. So now let me clearly formalize the screening methodology. So roughly speaking, the screening methodology is based on this type of criterion. Okay, so we look for the set of indices which maximizes this type of criterion. So here D is the association measure. So we will specify this measure later. So here you've got the output, Y, the target, and X, the feature. So S is the set of the selected feature indices. So as I mentioned, the drawback is the tendency to select the redundant covariates, because basically there is no feature-feature relationship to select the features. So there is an efficiency issue. So to fix this issue, as I mentioned, the MRMR methodology, so the minimum redundancy, maximum relevance method was developed. So by adding this feature-feature relationship to the original maximum relevance criterion. Okay, so this can be seen as a penalization of the original problem. Okay, to particularly target this redundancy issue. Okay, so now our proposed the proposed methodology that we have considered is within this MRMR approach. Okay, so now let me describe in more detail this MRMR methodology. So we can actually rewrite the MRMR algorithm with this criterion, okay, over these beta parameters, which can actually be relaxed as this continuous optimization problem, where the theta parameters now are non-negative parameters, and they are assumed to be sparse. So this is the key assumption in our methodology. So the assumption of sparsity, which means that a subset of features is truly important. Okay, so what we're going to do is that on this optimization problem, this criterion, we're going to add what's called a penalty function in order to generate zeros in the parameters. Okay, in order to model this sparsity assumption. So now the choice of this distance, this association measure, the choice of D is an important issue in practice, okay, because we need to empirically specify an association measure D. To do so, we chose the H-seq association measure. So the H-seq, Hilbert-Schmidt independence criterion measure. So it's the specification of the H-seq is lies within the reproducing kernel Hilbert space framework, okay, the RKHS framework. So that's why the H-seq measure depends on these kernels, phi and psi, which are assumed to be symmetric and bounded. And the definition of H-seq depends on the covariance operator. Okay, so if you're interested in such measure, you can find much further details in greater than cohorts or song and cohorts. So this quantity is the association measure, and this is this measure we chose in our analysis, okay, to specify this D function. The point here is that this quantity, HSIC, is a theoretical quantity. Okay, it depends on this expectation. Okay, so in practice, using the sample of observations, we're going to replace these expectations by an estimator. So that's the estimator of this HC association measure turns out to be this quantity, which is a V statistic-based estimator. Okay, so here this is a function of these L, H, and K matrices. So here the point is that these L and K matrices are these so-called Gram matrices. So they are functions of these counts. So this quantity is a biased estimator. And so we're going to replace in this criterion, this D association measure, we're going to replace them by this V statistic-based estimator. So here is the main criterion. So the MRMR optimization problem, I reminded here, is given by this problem. As I've mentioned, we replace the D association measure with the HSIC association measure. We take the V statistic-based estimator, and we end up with this criterion. So this is the Frobenius norm. We take the square of it. And in order to foster sparsity, in order so to perform feature selection over the nonlinear transformation of the HSIC association measure, we add this penalty function. Okay, so this penalty function, I'll provide more details later. So basically, this penalty function is a norm over the parameter theta, which is non-differentiable at the origin in order to foster sparsity. And it depends on lambda. So it is known as the tuning parameter or the regularization parameter. So it enforces a specific type of sparsity structure. And lambda depends, the calibration of lambda depends on the sample size. It's quite important. It's a function of the sample size. So actually the problem can be viewed as a regression-based problem. But of course, it's important to emphasize this point. It depends on the kernel, on the source of the kernel, which enters in these L and K functions. So U is an error term. All right, so now let me clearly state the penalized criterion that we considered. So the penalized criterion is given by the following problem. So the sparse HC criterion is defined in here. So we have, we look for the argument theta, which minimizes this loss function. So Gn is the V statistic-based HC criterion. And here we've got our penalty function. So this penalty function is coordinate separable. So here Gn, I emphasize this, Gn is a V statistic-based criterion. The penalties that we have considered are the lasso, which is convex, and these non-convex penalty functions, the bridge, SCAD, and MCP. So the points in the theoretical analysis, so we're going to look at the behavior of theta hat. So the point here is to use the asymptotic equivalence between V statistics and U statistics, because both quantities, V and U statistics, are very closely related, actually. So just that the V statistics are biased. So the U statistics corresponds to the unbiased version. So we're going to derive the U statistics representation of the V statistic-based loss function, Gn, so that we are in a position to use the theoretical properties of U statistics. So the theory for U statistics has been developed, was developed a long time ago. For example, you can look at Serfling, Hoeffding, or Lee. And the key ingredient when we look at the asymptotic distribution of a U statistic-based criterion is the variance of the U statistic. It's a key point. Because depending on some technical conditions on the variance, when you look at the asymptotic distribution of the U statistic, you may end up with a Gaussian or a summation of chi-square distributed random variables. So we need to carefully check the conditions to ensure what's called the non-degeneracy of the U statistics loss function. So here is the U statistic based criterion. So ln is the U statistics version of the V statistic based loss function Gn. Here the kernel L is a degree 4 kernel. Okay, so we're going to look at the asymptotic theory based on this loss function, so which depends on the parameter theta. So that's the criterion that we end up with is this one. So we assume that the population level criterion ln is uniquely minimized at the parameter theta 0. So the kernel that we obtained is given by this formula, which looks quite complicated. But to do so, we replaced the we used the U statistic estimator of the HSIC, which is provided by a Song and coauthors. Okay, and we ended up with such a U statistic based criterion. So the contributions are the following ones. Our motivation is to fix the redundancy issue and to provide a general framework based on U statistic in order to perform feature selection. We've derived also the asymptotic properties of the U statistic based sparse estimator. And we have illustrated also these results for numerical experiments and the relevance of the proposed method based on real data. So let me say a few words on the theoretical properties of the U statistic-based sparse estimator, sparse HSIC estimator. So under suitable assumptions, regularity conditions, when lambda n, so the regularization parameter, which depends on the sample size, we have that the penalized estimator converges to a certain parameter, theta 0 star, which is not the true parameter. Because of the penalization, there is a bias coming from the penalization. Okay, and this P function is provided in here, depending on which penalty function we actually look at. So if, of course, lambda n goes to 0 asymptotically, then the estimator is a consistent one. We've also derived an asymptotic probability bound for the penalized estimator. Here is an asymptotic distribution for a specific convergence rate of the regularization parameter, lambda n. So it looks quite complicated, this G function. Indeed, it is. It looks complicated, but the interesting point here is to look at the lasso penalty function. Here, this coefficient here will imply that the lasso does not allow you to truly recover the important features. So that's the drawback of the lasso, because it is convex. It is convex with respect to the parameters. So all parameters are equally penalized penalized with the same rate. So there is a bias inherent to the lasso. And we've also derived the oracle property. So the oracle property basically tells you that your regularization procedure can recover the true subset, the true sparse subset, and your estimator, the M estimator, is asymptotically normally distributed. So here, this is for the non-convex scaled MCP. So for specific regularity conditions, I will not enter into details. Basically, here we've got these two properties. So here the identification of the true sparse support. So A is the set of indices for which theta is non-zero, so the sparse subset. And here we've got this asymptotic normality distribution. So maybe let me illustrate the relevance of the method using a real data experiment. So that's what's interesting actually, to compare our method with alternative competitors. And here more precisely, we've compared our method, so the sparsity criterion, with the distance correlation, which is also commonly used approach for screening procedures. So the distance correlation and the theory for the distance correlation was proposed by Lee and co-authors. In particular, they proved what's called the sure screening property, which means that so asymptotically, all the truly important features can be selected with probability approaching 1. So this property, the sure screening property, is different from the oracle property that we have looked at, because we optimize with respect to the parameters theta. Okay, so it's a little bit different, the concept of sure screening and oracle property. So the real data experiment that I will show you will highlight the benefit of fixing the redundancy issue. So the real data sets that we've considered are the COIL and the ILPD of UCI machine learning repository data sets. So the COIL data set is typically a high dimensional data set because there are more features than observations. So we run our optimization problem, the penalized optimization problem. We've run the distance correlation based feature screening procedure, and we ended up with such mean classification accuracy results. So on the horizontal axis, you've got the number of selected features, and over there on the y-axis, you've got the mean classification accuracy. And in dashed pink, this is the competitor, so the distance correlation. And our proposed procedure is reported with these solid lines. So depending on the penalization method. So the first remark is that our procedure allows for better mean classification mean accuracy. Except so for the COIL, indeed the lasso does not perform pretty well, which somehow makes sense because the lasso again does not allow to properly recover the sparse support. But for example, the MCP or the SCAD, the non-convex penalization procedure behave pretty well, and the same remark also holds for the ILPD procedure. So the method actually works pretty well, empirically speaking. So let me conclude this presentation with the contributions that we proposed. So we proposed now a penalized use statistic-based M estimation criterion for feature selection in order to deal with the feature problem And we've derived also the large sample properties and illustrated the relevance of the method with several real data experiments. And for the future work, so we would like to develop also a criterion which is kernel free, because the main drawback that you may raise is that we need to specify the kernels, which may be a problem actually. So we would like to get rid of this issue. So for example, we could consider the distance correlation and integrate this association measure in our framework. And also we would like to establish the hierarchical property when the number of parameters diverges. And we would like also to go back to the standard feature selection methodology using the the maximum mean discrepancy, or the HSIC, and apply the knockoff technique in order to perform post-selection inference. Okay, so that's it for my presentation. So if you've got any questions, I'd be more than happy to answer them. Thank you very much.
Okay. Thanks, Benjamin. There's like a question in chat window.
Well, so the question is, why did you use a v-statistic-based estimator in statistic and ended up using a new statistic alternative in theoretical analysis? So v-statistic basically is equivalent to a u-statistic asymptotically. So we made our analysis asymptotically. So when n goes to infinity, and a broad range of results are established for u-statistics. So asymptotic normality, uniform convergence also for u-statistics. So we use these results in order to establish our results. So basically, once again, there is a square root n equivalence between a v-statistic and u-statistic. Okay, so that's why we directly consider the u-statistic. But we actually, in the proof, we could handle the difference between gn and the ln function, the u-statistic based function. It goes to zero, basically, this discrepancy, because of the equivalence. So that's why we first consider the v-statistic based criterion, and this v-statistic based criterion is equivalent asymptotically to the u-statistic representation. So I hope it does answer the question. Thanks. Any example of practical applications with model explainability, interpretability? That's a good issue. It's something that we actually would like to think of in the next the next project, when we think of a kernel free criterion, where we don't need to specify the kernel. But in terms of interpretability, I don't know if you, Makoto, you have maybe more intuitions also on that point.
Yes, so for the explainability, we have used the H cluster for the graph neural network explanation. And we are trying to use the method for various types of applications. So we are currently working on it. And so actually we got something good results, but still like there's some gap between the interpretation, because even if you can get the good features, that is good prediction accuracy, but still the results is sometimes not make sense. So this is like still we don't know how to improve, but we are currently working on it. So is this like I answered well? Okay, I hope I answered well. Okay, thanks.
Thanks.
Yeah, thanks for the question. So if you have any further question, you can just post it to Q&A, and we can answer later. Okay, so then Dinesh, please start your talk.
So can you hear my voice clear?
Yes.
Yeah, okay. So I am Dinesh Singh, a postdoctoral researcher in Recane AIP. So I'm going to present one of my recent work for feature selection network on high dimensional biological data. So this is a joint work with other members of the Recane. So as Makoto explained, and also the Benjamin explained, that biological data is generally very high dimensional, and the number of samples are very, very limited. So we call it like HDSS, the high dimensional data with a small number of samples. So for example, like gene expression data, and in spite of very less number of samples, it contains complex nonlinear patterns which cannot be find out by the linear models. So we need definitely need some nonlinear models. So on the other hand, nowadays, like deep neural networks are giving very good results for various tasks in computer vision and natural language processing. But because of very less number of samples available and the high dimensionality, so they are not widely used for the task of feature selection purpose. Because in such kind of setting, they can easily overfit because they have very large number of parameters. And when we have a large number of parameters, we need more samples to uh, train them efficiently. So now I will just focus on the second part, like how we can apply the deep neural networks for such a problem where very limited data is available. So the existing methods are linear, or if there are some non-linear functions are there, so their non-linearity is limited to the kernel functions, as recently Benjamin told. So so Benjamin already give very good introduction to the shallow networks, so I will not spend more time on this one. So rather I will just focus on the issues in the existing feature selection methods. So the existing feature selection methods are either linear models, they are finding out some sparse solutions and uh, setting most of the features to 0 so that they can be excluded for the further analysis of in the model. Or if there are some nonlinear methods are there, so there and this nonlinearity is limited to the choice of kernel functions, which is again very hard to say that whether it's the intrinsic the complex, it can find out the complex pattern exist between the features and the target variables. If we talk about the arbitrary nonlinearity, so autoencoders, which is a part of deep neural networks, can find out arbitrary nonlinearity. But they cannot be readily applied for feature selection tasks, as the feature selection task is a like a discrete optimization problem. And when we make a layer as the feature selection layer, so then this discrete feature selection actually break the back propagations, and we cannot back propagate the gradients in order to learn the selection layer. And apart from them, most of the times, like we are selecting features, it's not only like that we are selecting features based on some nonlinear complex patterns, but those selected features should also explain all the other features also, so that we can say that they are the good candidates among the all the features. So many times, the existing methods are just focusing on the like linear combinations when they are doing the reconstructions. So this is another problems. We are going to we are trying to address most of the problems explained just now. So here our objective is to develop an end-to-end neural network based method for nonlinear feature selection from the high dimensional data sets where very limited number of samples are available, like gene expression data. Okay, so there are some works already done by using the neural networks for the feature selections. So if I can broadly classify those works, so I can put them into three works. So the first work is training the normal neural networks by adding some regularization terms in the loss function, and then so that our network has more sparsity, and then after training they did some kind of analysis that what is the effect of the input features on the target variables, or what is what is the value of the gradients for a particular input image, input features. So by doing such an analysis, first of all, so this kind of methods actually experience some degradation in the performance after the selections, because the training is different, and after the training we did some feature selection, so that network is not giving very good result. And that second category is like that many methods like attention network and deep pink and cancel out, and recently that STG based methods, they actually introduce one extra layer which is called like feature scoring layer. So this layer actually represents the score of each features, and this is also trained using back propagation. So here the input features are simply there is a element wise multiplication between the scores and features, and then that results are fed into the rest of the network. So but the biggest problem is that in such a network, so it is very hard to obtain a sparse solutions, and most of the times all the features are equally high or low, and even many times there is a no correlation that features for whom the score is very high, so actually that is more correlated, because that is actually decided by the later layers, so how they are going to use that features for the target prediction. So that is one thing, and another solution another issue is like that there are very limited, when there are very limited number of samples, so we cannot train this model with very good generalization ability. So there are third category where and also in such kind of features we don't have the control on the number of features we are going to select. Actually all those values which has non-zero values, so we need to select them, and if we do not select, so actually again there is a degradation in the performance. So then we have like some jumble softmax based methods like concrete autoencoders, where they introduce the feature selection layer, and this feature selection layers actually has the exactly that many neurons, the number of features we want to select, and each actually a neuron in the selection layer select one features among the many features. So here, if we see that this is a selection task, and that this matrix actually becomes a one hot matrix because of this discrete nature of feature selection task. So in order to apply the or the back propagation of the gradients, so there is a the authors use actually jumble softmax, which is a continuous relaxation of the one hot vector. So after that, actually the forward pass can have we can compute by the use of the relax values. So and even after that, during the back propagation, so the gradients cannot be passed, but then they use the like reparameterization trick to stochastically train those features. So again, this method works well when there are large number of samples available, but again, for the very less number of samples, so this methods like performance is not very reliable. It's like very unstable training. Also, this method is unsupervised because they are focusing only on the reconstruction of the features. So while when we use the supervised learning method, so they are performs better than the unsupervised features always. So this is one thing, like how feature selection neural network can be used for feature selections. But again, so these features, those networks are not able to train with a limited number of samples. So in order to train them on the limited number of samples, so we need to reduce the number of parameters, because when the number of parameters are large, and that is because of the mostly the first and the last layers in the autoencoders, which is high because dimensionality is very high. So this high dimensionality actually, because of this high dimensionality, the network suffer from this curse of dimensionality even after applying so many regularization constraints. So if we reduce the number of parameters we are learning, so then we can stabilize the training little better than the large number of parameters. So there are several tricks how we can compress the neural networks, but they are largely applied on the means post training. So when we are talking about during the training, so and for the which are very efficient to be readily applied for the feature selections, so I find out these two methods are more suitable. So first is the hashnet. So in this method, actually authors are not learning all the weights in a layer. So actually they are treating a layer with large number of parameters as a virtual layer, and instead of all the features, they are learning small buckets. And now, because the neural network is also known for the inherent redundancy, so they are exploiting that inherent redundancy. And so they using a hash function, they group similar features and then use the same weight for all those connections. In this way, the number of parameters reduce, and they can easily back propagate the gradients through that, and they can update these weights. So but this weight update is collective for all the connections. So in this way, these methods actually can able to reduce the number of parameters, but like it's like the freedom of parameters in the virtual layer is like limited to the number of unique parameters in the hash or the hash size. So this is the one of the drawback of this one. And also in this method, actually that hash function is mainly assigned based on the initial values. So there is no dynamic grouping of the weights. So these are the two drawbacks in this one. Then there is another network proposed in 2007. So this is diet network. So actually this network use two tiny networks to train. So it's actually learning another small networks to predict the weights of the large or the fat weight matrices. So generally, when we are using the autoencoders, so we have fat matrices in the selection layer and the reconstruction layer. So these two, so in this method, they also target these two methods. And in order to predict these functions, they actually use the dimensions to predict the weights connected to that particular dimension to all the hidden neurons in the next layer. So this method, unlike that hash networks, has the full spectrum of the weights, and there is no such quantization of weights. So there is more freedom in learning the weight of the virtual matrices. And so this is, but this method is actually applied for the for the classification task and cannot be applied for feature selection. So they are using all the features for even predicting the weights and also the making the final decision in the classifier. So so by considering all these problems, like we designed one our architecture. So in this one, so we also put like one selection layer followed by one encoder, which actually encode the selected features into a like nonlinear transformation. So those hidden outputs actually then we use for the classification of the task. And because if we use only the classifier, so this is enough for the supervised network. But in this case, actually we can still, so although we reduce the number of parameters by using the settings similar to diet network, but still the number of samples are too less, and we can easily overfit. Now, in order to stabilize the network and also to focus on the selection of the features and the learning of an like intermediate space, such that it's also very suitable to like predict all the other features. And so then if they are also able to like explain all the other features, then we can say that yes, these are the good candidates. These features are the good candidates representing the entire data sets. Also that nonlinear representation can say that, okay, this is the actually the intrinsic space where we can separate them. All the classes we can separate easily. So in this network, also like we put the decoder as a like mirror network of the encoder, so that whatever nonlinear transformation from all the features to the hidden representations we are learning. So a reverse nonlinear like model we are learning, so to like decode those features. So in this entire network, so the first layer and the last layer, the first layer is the selection layer and the reconstruction layer. So these two are very high because our data is very high dimensional. So in order to reduce the number of parameters, so we learn two separate parameters. So one is the selector weight predictor. So here actually we use one embedding for the each features to predict the weights connecting that particular neuron to all the other neurons in the like say in the encoder. Similarly, in the other the last reconstruction layer, so here we use a reconstruction weight predictor. So again, this is also trained on the same feature embeddings. So so like for each feature embedding, it actually predicts the weight actually connecting all the like neurons in the last layer of the decoder to the each neuron into the reconstruction. So this is a reverse in comparison to the selection layer. So in this like entire network, so then we use the class cross entropy, which is the supervised loss, and that reconstruction error, which is like unsupervised loss. So this actually the combining these two also learns the very features which are very good candidates, and as well as stabilize the training, and also the reduced number of parameters using that weight predictor networks also reduce the number of parameters, which further stabilize the like overall training behavior of the network. So in the selection layer, again, we use the jumble softmax based method, and we train it using annealing methods. So where we set the temperature initially to a high temperature and reduce it over the epochs, and finally when the temperature goes towards the zero, so these values actually results into a one hot vector. So then in order to like backpropagate the gradients, so we also use that stochastic gradient and this reparameterization trick. So in this like in this function, that again those weights are actually coming from the weight predictor network. So because our actual the selection layer is a like virtual layer. So after getting all the weights for all the input neurons connecting to all the hidden neurons, so we then find out that like relaxation of the one hot vector. So apart from that, so for training it is enough, like, but what we observe in such a network, when we are training with limited number of samples, and each neuron is free to pick any feature from all out of all the number of dimensions. So it finally end up with selecting the redundant means same features more than once. So in order to handle this situation, so actually we replace the argmax function with a unique argmax function. So here actually we select the unique max values out of the like whatever are the max values. If one features has the max value at the two neurons, so then we actually select the next max in that one. So in this way, actually that our network feeds the unique features into the rest of the network. So if I talk about the empirical results, so we evaluated the performance on the several benchmark data sets, where we have the dimensions of 1,000 to tens of thousand, and the number of samples are less than the 200. So in such a settings, when we train our feature selection network with k equal to 10, so our methods outperform the other methods. So here CA, because the CA is an unsupervised method, so in order to provide a fair comparison, we also add one like softmax layer similar to our function, and these two are the like shallow network like kernel based methods. So when we are selecting very less number of features, so again the number of parameters in the selection layers is very less. So because of that, our models is like more stable and outperform all the features. So when we are increasing the number of features, then like again number of parameters in the selection layers are increasing, and the behavior is similar to that of CA because of the large number of parameters. So while still, if we compare with the kernel methods and the diet networks without selecting features based on all the features, so our methods actually perform better than these two methods. So the another thing is how is the training behaviors, as I was focusing on like that if the dimension is more and number of samples are less, so training is not like very stable. So in this figures we plot the test classification accuracy and train classification accuracy over the epochs. If we see that in this one, that black curve shows that shows the performance of the diet network. So diet networks training performance is much better than any other function. So here again that CA, because of large number of parameters, so its behavior is very unstable and it's almost overfitting. While there is a lot of zigzag in the FSNet, but finally over the epochs, it slowly reaches very closer to the FSNet. And when we are talking about the test, so both the test accuracy of the FSNet is not in the correlation with the training accuracy. So means even diet network is going to be a little overfit because it's using all the features. And then another is this CA, the test accuracy is again just kind of random, somewhere high and low. While FSNet again the test accuracy is also increased gradually and is also very in the very closer to the test accuracy. So we can say that so there is some generalization in the FSNet that whatever is the train, so it sustains that during the test cases also. And the same behavior is almost same behavior can be seen in the other data sets also. So when we are talking about the explainability, so our reconstruction error is very less in comparison to the other methods. And when we are talking about the interpretation of the selected features, so here I present the features selected randomly and using supervised CA and FSNet. If we see that random features, there is no clear pattern where it is higher or where it's lower. CA has a little higher in one side and lower in another, but again, so there is no clarity. While for the FSNet, there are several features were selected where it's consistently low for the one class and consistently high for the other class. So also if we see the scatter plots, the test classes lie almost over the classes in that train. So in this way we can say that it's selecting very good features. Also, the mutual information among the selected features is very low for FSNet in comparison to other methods, and that's because of selecting the non-redundant features and with very and unique features. So our methods reduce the number of parameters by D by B, where B is the bin we selected for or the size of the embedding, and D is the original dimension of the features. So for the used data set, actually it compresses from 25 to 100 times, and the number of parameters are less. So we also apply this for that inflammatory bowel disease, where also it performs very good and outperform the SVM and diet networks. And the same training behavior can be seen on this one. Okay, so in this way, so we present FSNet, which is an end-to-end trainable deep learning-based feature selection method for high-dimensional data with a small number of samples. So in this features, actually, we use weight predictor network to reduce the number of parameters and reconstruction to stabilize the training. So by using that these two settings, by reducing the number of parameters to train and the reconstruction loss, so we are able to train this one, which can be evidenced by the experiments on the several these high dimensional data sets. Thank you.
Okay, thanks, Dinesh, for the talk. And so actually, there's two questions. So could you please first read the questions and answer?
Is tau hyperparameter in practice are most neuro forced to be one hot vector? Does it mean each neuro will select only one features? So yes, tau is a hyperparameters, but generally we set it to very high, like 10, and then we gradually reduce it through annealing schedule to a very low temperatures, like 0.01 something. And yes, yeah, finally, when tau tends to like 0, so most of the these features will result into a one hot vector or very near to the one hot vector, and finally our this unique argmax functions or argmax functions actually converted to a one hot vector. So the second question is, what is the motivation of using nonlinear neural network to perform FS? If we merely want to improve the model fitting ability, nonlinearity, why not using some kernel-based methods? Yes, kernel-based method can be used, but again, that nonlinearity is again limited to the choice of the features. So you cannot find out the arbitrary transformation into the functions where we can say that, okay, within this space, our features are like better classifying the target variable or whatever. So that's all.
Okay, thanks, Dinesh, for the answering. Okay, so I think it's good to move to the other talk. So thanks, Dinesh, for your talk. It's nice. And Tom, could you please prepare for your presentation? Tom, could you start?
So next, I will talk about an introduction on this slide, consistent geometry. The tree consistent is a special case of optimal transport. Optimal transport is a natural geometry for probability measure. The optimal transport can trace back to monks in the 18th century, when workers want to optimize their effort to move a bag of sand from one place into the other. The optimal transport have a wide range of application from economics, data science, to applied math or full math, to name a few. Notably, the Nobel Prize in Economics for Catterick and Kaufman, and recent few medals for Villani and later for Figari. There are many open problems in optimal transport, ranging from theory to practice. Optimal transport can be applied for image legitimate data from dynamical system, material data. For example, here is the relative atomic position in molecules, documents, network architecture, or position diagram for topological data analysis, statistical model. So let's consider an example for optimal transport where we want to find the optimal way to transport donuts from 3 bakeries to 3 restaurants in the map. So more precisely, each bakery can make some donut boxes, let's say 20, 50, 30, while each restaurant demands some certain donut boxes, let's say 30, 60, and 10. And here are the transportation routes to transport donuts from the bakery to the restaurant. We summarize the transportation problem in the left figure. There are two main ingredients for the optimal transport problem. The first one is the cost metric or the ground metric. The Ix here is mean the cost to transport one donut box from the bakery A to the restaurant X. The second component is the transportation plan. We have several plans to transport donuts from the bakery to the restaurant, and here is the specific plan which is proportional to the demands of the restaurant. So each bakery will transport 30% for X, 60% for Y, and 10% for Z. And the goal of the optimal transport is to find the best transportation plan. So bakeries and restaurants can be considered as the probability measures where the supports are locations of the bakeries or restaurants, and the mass or weight are the amount of donut boxes which a bakery can make or a restaurant demands. We did not M for the ground metric and T for the transportation plan. The goal is to find the optimal T. Formally, the optimal transport distance is equal to the minimal total cost to transport the donut. Satisfy some constraints. The transportation plan satisfies the total amount which each bakery can provide, and it also satisfies the total amount which each restaurant can receive, and the transportation for any bakery to any restaurant should be non-negative. However, the complexity of optimal transport is high, supercubic, or M/3 log n. Moreover, optimal transport distance is indefinite, so it limits the ability to build valid kernels upon the optimal transport geometry. One idea to speak of the computation of optimal transport is use the entropic regularization proposed by Couturier in 2013. So it can reduce the complexity into quadratic of n squared. N is the number of supports in the measure. However, syncon is still indefinite at optimal transport, and syncon is not a metric since it doesn't satisfy the identity axiom. The syncon between mu and mu is not equal to 0. The other approach to speak of the computation of optimal transport is based on the univariate optimal transport. More precisely, the slide Wasserstein projects the support into one-dimensional space and relies on the closed form solution of the univariate optimal transport. So it will project C, B, A, X, Y, Z into the line. In practice, this case the one-dimensional space may happen inside the bakeries and the restaurant are in the same street. So we only need to sort supports ascendingly and then transport donut following from the left mode to the right mode. So we start with the left mode. For bakery C, we will transport 10 boxes to restaurant Z and the remaining 20 to restaurant Y. For bakery B, we will transport 40 boxes for Y to fulfill the demands of restaurant Y, and the remaining 10 boxes for X, and for bakery A, we just transport the on 20 boxes to X to fulfill the demands of restaurant X. So the complexity can be reduced into O and log n, which we pay to sort the supports. Another advantage of slide Wasserstein is that the slide Wasserstein is negative definite. So it allows us to build positive definite kernels up on the slide Wasserstein distance. However, due to using the one-dimensional projection for supports, this approach is affected by the curse of dimensionality. The one-dimensional projection limits the capacity to capturing the high-dimensional structure of distribution. And our proposed approach is based on tree, where we sample tree structure from support data points. Therefore, we can remedy the curse of dimensionality in slide Wasserstein. Moreover, the tree Wasserstein is a generalized version for slide Wasserstein. Indeed, if we choose a tree as a chain, the tree Wasserstein is equivalent to the slide Wasserstein. We show that the tree Wasserstein has a closed form for computation, and its complexity is linear to the number of edges in the tree. Moreover, tree Wasserstein is also negative definite as in the slide Wasserstein, so we can build positive definite kernels up on the tree Wasserstein distance. So the tree Wasserstein admits the closed form like this one. It is assumed over edge. For example, if we consider this edge, the W is the weight of this edge, and V is one of the nodes of the edge, but farther away from the root. So for this edge, V is this node. Gamma V is a subtree rooted as VE, and mu of gamma V is the mass of mu in this subtree. For example, here in this subtree, for the measure mu, we only have the support C in this subtree. So mu of gamma VE for this XE equal to 30. One assumption of optimal transport is that the total mass of measure are equal. However, in practical application, measure may have different total mass. For example, the bakeries can provide more donut boxes than the demands of the restaurant. Or the restaurants can buy more donut boxes than the bakeries can provide. Or summarize, the total mass of measure are different. Secondly, we may want to partial transport donut. For partial transport, we mean that only M donut to transport from the bakery to the restaurant. So we formulate the problem at the entropy partial transport. The first two terms are the entropy to measure the difference between mu and nu with the first marginal and the second marginal of the transportation plane gamma. Here we have the constraint, the total mass of gamma equal to m for partial transport. The first term here is just the standard optimal transport, but here we have the constraint for partial transport with the total mass equal to m. So more precisely, we use the weighted relative entropies for calligraphic F1 and F2. So we have the weight here, it's just simply the non-negative wave, and F1, F2 are the entropy function. For example, here the total variance, the total variation entropy. We next form the Lagrange multipliers conjugate to the partial transport, the total mass of gamma equal to m. So now we use the Lagrange multiplier. So we can show that the EBT is equivalent to the standard optimal transport between mu hat and nu hat. So here mu hat and nu hat have the same mass, and with the cost new cost C hat build up on the cost original cost C. So since it's equivalent to the standard optimal transport, we are easily to derive the dual formulation for the EBT. A key observation is that fx equal to fr, which r is the root of the tree, and plus with the integral from r to x of a g function, and g is a elliptic function. So we propose the regularized entropy partial transport by replace the set L here by the L alpha. So this contrast is equivalent to the G p elliptic if the G is p elliptic function for the when we use this form, we derive the form for f, and the range contrast here we only keep for the root. We also note that when alpha equal to 0, L is a subset of L0. The regularized EBT admits a closed form solution. So for this term, it is similar to the three-quarter stand for when the measure have the same mass. And here we have two other terms, sum of the mass and the different mass. To the best of our knowledge, this is the first closed form solution for unbalanced optimal transport with zero measure. Even for the univariate unbalanced optimal transport, all supports are in one-dimensional space. It has no closed form solution, and its complexity is quadratic in worst case. Furthermore, our regularized EBT is also the first unbalanced OT having negative definite properties, which allow us to build BD kernels. We also derive the bound for the regularized EBT with respect to the standard EBT without regularization. So here we illustrate the approximation for the regularized EBT. In the left figure, we vary the elliptic constant for the function, the wave function W1 and W2. So A1 here is will vary from 0 to P with set equal to 1. We observe that the approximations of the regularized EBT is improved when the elliptic constant is close to B. For the right figure, we set the elliptic constant of the functions W1, W2 to B. We observe that the regularized EBT is almost identical to the standard EBT regardless the value of lambda. We also derive three approaches for other problems, but I will skip them due to the limit times. So the tree was a Stanbury Center where we would like to find the probability closest to n given probability, and the other ones is when measure asymptotic in different space. So the standard optimal transport is not valid anymore. So a popular ones is the Chroma-Quasar-Stan, but the Chroma-Quasar-Stan is a non-convex colligated quadratic ramming and is NP-hard in for arbitrary input. So we propose the flow-based alignment approach with the complexity of n squared, much faster. We next show some application of the three-Quasar-Stan geometry. So we recall that the optimal transport is indefinite. So we can see that the optimal transport works well for document classification, but its performance is affected for topological data analysis. We also note that for document classification, the dimension of support is 300. For topological data analysis, the dimension of support is 2. We see that the slide consistent is suffer. Its performance is suffer for high dimensional application. So it performs worse than the optimal transport. But for low dimension application, the slide was sustained. It performed better than the optimal transport. And our tree was sustained. This slide was sustained. It performed favorably with other baseline. Since it also a negative definite, as in the slide was sustained, and it can remedy the curve of dimensionality as in the slide was sustained. And tree was sustained also fast for computation. You can see that it's very fast in computation. We also applied tree was sustained for neural architecture search problem for deep learning, where we regard the network architecture at level directed graph, and our approach leverages the tree was sustained kernels for Bayesian optimization to automatically find a good architecture for network. So this is joint work with many people, and I would like to thank all collaborators, and thank you for your attention.
Okay, Tam, thanks for your talk. And from the audience, do you have any questions for this one? Okay, Tam, there's one question in
So
Q&A.
there is a question. Can you provide the details of projection on lights or trees? So for the light, it just the slide was sustained. It just simply choose a random slide, and there are many variants of the slide was sustained. It may choose the mark slide. So the mark slide was sustained if we choose the direction to have a maximum value for the slide was sustained. And for the tree, actually we can sampling the tree like this one. So here is the partition space tree matrix sampling. So for low dimensional space of support, assume we have the on data points in the hypercube, and then we partition them to form the tree. So first we partition into 4 parts. So this part, we have this node, this part, we have this node, this part, we have the other node, and hierarchically partition them. So we have until the end. So we have the tree. For high dimensional space of support, we replace the partition by the clustering by to sample the tree. I hope this answer your question.
Okay, so I think we are slightly delayed. So let's thanks, Sam, for your talk. And Hector, could you please prepare your slide?
Okay, well, good morning, good afternoon, or good evening, depending on where you are. So my goal is to develop methods to better understand the genetics of diseases. Essentially, you can make 2 big categories of diseases. One of them are Mendelian, and Mendelian, we could say that they are simple. They are like tossing a coin. If you get a heads, you win. If you get tails, you lose. In the same way, Mendelian diseases depend on a single alteration in your genome, like a mutation, a particular mutation that runs in families that will determine whether you will have disease or not. On the other hand, actually, what I study are so-called complex diseases, which, as the name implies, they are, complex. You can imagine them as playing a poker game. Of course, you are given a hand and you have a set of cards that will interact with each other, but that in itself will not determine whether you will win or lose. It depends on how you carry yourself on the table. It depends on what everyone else has. It will depend on how everyone can bluff, etc. So specifically, the question that me and many biologists ask is relatively simple, which is which card makes victory more likely. Obviously, if you have an ace on your hand, it's much likelier that you will win that round than if you have a 2. And specifically, I want to study how using prior information that we can model as networks can help. This prior information is things that come from experiments, gene ontologies, annotation in databases, etc. So until now, I've been talking about cards and poker, but actually what we study are called SNPs, which stand for single nucleotide polymorphisms. SNPs are like the smallest alteration that you can have on your genome. It's basically in one position, a share of the population will have, one of the nucleotides, one of the letters A, T, C, or G, and another share of the population will have another one. It's such a tiny change in the genome, and in consequence, each of these SNPs have a very, very small effect on the final state of disease or not. However, when you aggregate the effect of all the SNPs together, then, well, you might have some increased chance of developing a disease, or on the other hand, some protection against some diseases. So we study the genetics of complex diseases in this very straightforward approach called genome-wide association studies, which we often refer to as GWAS. Essentially, we take a couple of thousands of people who have the particular disease under study, which we call cases, and another couple thousands of controls, people that are healthy and come from the general population, from the same population as the cases. And then we do what we call genotyping. We measure which, for a given set of SNPs, we measure which SNP, which particular variant A, T, C, or G has each of the samples. Then you basically end up with a very large table, and then you just have to conduct a SNP-wise statistical test, often just a simple chi-square or a linear model. So despite the simplicity of the experimental setting, GWAS has multiple challenges, and people like me who study how to develop new methodologies for GWAS are trying to address. Specifically, I will just focus on one today, which is the lack of statistical power. As I said, in a typical GWAS, we study on the order of a couple thousand samples, but we genotype many, many more SNPs. So basically, we end up with matrices that look something like this, where this is a pretty ugly matrix. It has tons of statistical problems, the curse of dimensionality, etc., etc. So essentially, that completely kills our statistical power. That's also because, well, we are very likely to get some spurious correlations, so we have to be really conservative in what we consider significant or not. Typically, we use a Bonferroni threshold. And of course, that's compounded with the fact that most of the SNPs will have very, very small effect sizes. So yeah, we are pretty unlikely to detect them. So going back to, or better said, starting with my actual work, I studied the genetics of familial breast cancer, which is basically, as the name implies, is a breast cancer that tends to happen in certain families. And typically these are families where, a disproportionate amount of women had this disease. So we work on the Genesis dataset, which focuses on French women. We have around 2,500 samples, more or less evenly split between cases and controls. The cases are women that developed breast cancer and also had a sister that developed breast cancer in the past. So, so we are pretty sure there is a genetic component there, while the controls are just friends and colleagues of the cases. So essentially people of around the same age who share the environment, who share the same exposure to environmental factors, and yet they didn't develop breast cancer. And then we genotype 200,000 SNPs using the ICOX platform, which targets SNPs that are thought to be interesting for cancer-related, for hormonal cancers like breast cancer, prostate cancer, ovarian cancer, etc. After some pretty standard quality control, this is what we obtain. So these are called Manhattan plots and are a pretty common way of showing GWAS results. Essentially, on the x-axis, you can find the position of the particular SNP. They are just ordered in the genomic sequence. And in the y-axis, you have the association. And in this case, minus log 10 of the p-value. So the higher, the better. The higher, the more strongly associated. And then the red line just represents the Bonferroni threshold. So we conducted two kinds of experiments, one at the SNP level, as I explained before, and another at the gene level. And so the gene is the functional unit of the genome. And that just implies that we take sets of SNPs and we clamp them together and we test their joint association with the disease. So as you can see, we detect two peaks that are significant, and that's very encouraging because both of them are places, genomic regions known to be related to familial breast cancer in other cohorts. So that's great. But of course, we face the problem of, well, this doesn't explain all of the disease. And specifically, for instance, we find two regions that, as you can see, are pretty consistently altered. You can see the peaks, but they are not significant. But actually, these two regions are known to also be involved in familial breast cancer in other cohorts. So basically, our question is, if we integrate experimental information that comes from databases, wherever, and we model that using a network, can we do better than conventional GWAS? So then we started defining our experimental setting. Specifically, we took the HINT network, which is a protein-protein interaction network. This means that, well, we have genes, which are the functional units. These genes will produce a protein, which is, the molecule that actually carries out the work. And then when we have experimental evidence that two proteins interact with each other, like physically interact, then we establish an edge between the two links, the two genes. So essentially, we have a network like that where the edges come from experiments, and we score the nodes based on the statistical association that we find in the Genesis study. And then the problem becomes surveying this network and trying to find regions of it where genes that are connected to each other tend to have higher scores of association. So it doesn't matter anymore if they are Bonferroni significant, but it matters that they are consistently higher than what you would expect by chance. So there are many published algorithms in the literature to do that, and basically they came from different fields. They make different assumptions about what the solution looks like. They score the nodes slightly differently. I don't have the time to go into details, but basically we applied each of them to the network that I just described, and we obtained 6 different solutions, or rather 5, since one of the methods didn't produce any output. And well, the first thing you can see is that just by looking at the solutions, they are very different. And so yeah, we verified that these very different assumptions that they made at the beginning actually translated into extremely different outputs at the end. So, well, that was our first observation. Network methods are really heterogeneous, not only in the topology of the networks that we just saw, but also in what kind of genes they select in terms of their statistical association. You can see how methods like HotNet and SIGMOD seem to pick like a threshold lower than Bonferroni, but still there's like some sort of imaginary line which for what they will consider significant or not. Others like DMGWAS tend to select things all over the place, scones tend to select SNPs that are sequential to each other in the sequence, one after the other. We find a lot of variety. And when we actually look at the genes that are selected, unsurprisingly, they are also very different as measured by the Pearson correlation between these sets. So to address all this heterogeneity, what we did was to study the overlap between the different solutions. And encouragingly, we found out that if we selected only the genes that were selected by at least 2 methods, we ended up with a subnetwork that we call the consensus network that retains the nice properties that we find in the individual solutions, and then I will explain now. But also we find something that is manageable and we can actually visualize and study easily. So now I'm going to talk about these nice properties because, well, our second observation is that we find that network methods are boost discovery. Specifically, we find that network methods recover everything that a conventional GWAS found, basically this FEFR2 peak, but also they select genes that topologically capture properties that topologically have properties that are known to be associated to disease genes. Essentially, they are genes that tend to occupy central positions in the network. Also, they recover many known breast cancer susceptibility genes that have been identified in other GWAS studies, in other sort of experimental settings, and but not in Genesis. When we study their functional their functions via, for instance, a pathway enrichment analysis, we see that they tend to have functions that are relevant for cancer. And maybe the most important point is that network methods provide interpretable solutions. So we can just look at the network, and because there is some experimental information to back everything up, we can actually imagine mechanism of actions through which these alterations can lead to disease. So what we did was to look for the best GWAS study out there on breast cancer and see how well could we replicate their results. So we found the BCAC study, which we call a gold standard, and we put many air quotes in that because, well, it's not really, you cannot really have a gold standard in GWAS. Just by definition, there is no, we just don't know the real heritability of the disease. And also the experimental settings are not the same, the populations are not the same, etc. But with all these strings attached, it's a study that has 100 times more samples than our original study and 50 times more SNPs. So basically, we expect that they find most of the things we expected to find in our Genesis study. And so if we take as true positives everything that was bonferroni significant in BCAC, then we can do this precision and recall study. What we observe is that compared to a conventional GWAS analysis, which would be represented by this chi-square and plus bonferroni, network methods tend to have much higher recall at the expense of precision. Essentially, we are capturing more and more genes that were significant in BCAC at the expense of introducing other genes that were not as significant in BCAC. While that might look like a bug, we believe, at least to some extent, is a feature. And I want to exemplify this by showing this example on the consensus network. You can see how the whole network seems to be organized around this gene, which is the most central gene, COPS5. This is a gene that was not significant in Genesis and was not significant in BCAC either. It has a pretty terrible p-value. However, in other experimental settings, it was found to be overexpressed in breast cancer and actually also in other tumors. So we know it's actually important for cancer, and the network analysis finds it, but a conventional GWAS setting where you just look at the association of each of the nodes individually would never have found it. However, by using a network, we can actually see that, you know, this guide might be articulating the whole susceptibility mechanism. So lastly, what we did was to characterize the parameter spaces and biases of all of the methods. And of course, I don't have time today to go into detail, so I will just make two very general observations where there is room for improvement in these network methods. The first one is that the network methods were terribly unstable, meaning that when we ran them on a subsample of our original study that in our case contained 80% of the samples, yeah, the solution tended to change a lot for most of them, except for this guy, Heinz, which was pretty consistent. But still, yeah, they are doing pretty bad, especially in comparison with a conventional GWAS study. The second observation is that network methods tended to be pretty biased by network topology, meaning that they preferred genes that occupied central positions in the network. By central, I mean that if you take two random nodes and you compute the shortest path between them, well, central genes will tend to be more often in such a shortest path than non-central genes. So what we did was to do random rewirings where we take the network, but we swap the edges in such a way that the degree, the number of edges of each of the nodes is preserved, but the topology and the topology is preserved, but by swapping them, the all biological meaning is lost. And then we ran all the methods, and we saw how basically more central nodes tend to be selected even when the network means nothing. So yeah, our conclusions is that by using network methods, we were able to provide new breast cancer biomarkers. The solutions provided by the different network methods are really, really different, but they all share these nice properties, which I enumerated. So it seems that each of them seems to be capturing a different part of the mechanism of the disease. And lastly, that aggregating the results seemed to be a good strategy to end up with some manageable solution that provides a good set of biomarkers and preserves all these nice properties. If you're interested in our work, we published, well, the preprint is currently on bioRxiv, and currently it's under review in PLOS Computational Biology. And also I provide implementations of all 6 methods that can be applied to any GWAS study in this GitHub repository. Thank you for your attention.
Okay, thanks Hector for your talk. From the audience, do you have any questions for this presentation? So if so, please put a question to the Q&A. Also, if you have any questions, okay. So Hector, there's a questions. Could you first read a question, then answer?
Right. So he's asking, we have been working on improving Bonferroni by LAMP and MP-LAMP. Is it possible to use our results for your work? Okay, I mean, I will start with a disclaimer. I'm not really that familiar with LAMP, so there is that. I know some people are using LAMP in GWAS studies to detect epistasis, like high order epistasis, where this parameter space is even more terrible. So I'm assuming there is a potential there. But without knowing more, I can't be more specific. But LAMP has definitely been used in GWAS studies before, so I'm sure there is a lot of potential there. I'm also happy to continue this discussion in the future. Feel free to contact me.
Okay, thanks. And so for do you have any other questions for in our seminar? If so, we can maybe answer a couple of. Okay, so yeah, so if you come up with some question, please let me know. I have some advertisement in the end. So okay, so thank you again for attending our seminar today. Oh, okay. So there's another question. Hector, there's another question. Could you answer it if possible?
Sure. So I will first read it out loud. Hector, thank you for presenting attractive methodologies and results. I'm also working on GWAS. You said network analysis was unstable. I think it's a big problem when moving to practice in medicine. I agree. How should we interpret the results of network analysis when we apply these methodologies? Yeah, I agree. I mean, ideally, we would like to have a consistently selected set of biomarkers, right? However, I think networks are bound to be unstable for a long time just by design. So biological networks are known to be redundant, and that's just like that for evolutionary measures. Basically, if you have, several paths to transmit information, well, you want them to be redundant in case one of them, there is a mutation that sort of interrupts them, you still have other paths. So, and that's encoded in our networks, and that's bound to cause instability. I think there is room for methodological development there, but yeah, I didn't have time to address this in my presentation, but basically the way we address it on our work is we actually take different subsamples, we apply all the different methods in this cross-fold setting, and then we sort of take a stability consensus that, well, takes is basically like the consensus I presented, but in this subsample study, and that way we sort of address this problem. But for now, I don't have a better answer than that. Thank you for your question. It's really, really good.
Okay. So thank you very much for the questions. And okay, so this is the end of our seminar. Thank you again for coming to our seminar. So if you have any further questions after this seminar, please feel free to send us an email. So general things, maybe you can send me an email. For if you have any particular question, please feel free to contact each of the researchers. And so actually, this is a nice AIP seminar. And next week, we have a seminar by Function Analytic Learning Unit. After that, we have many other seminars. So please, those research seminars also great speakers and nice topics. So please register these seminars as well. Thank you very much for the, so this is it. Thank you.